we were discussing a few things having to do with the homeworks if you're just coming in now. So let me be clear what's going on with the homework. So everybody is supposed to be looking through and trying to make comments on the homeworks. And I'm sorry I haven't put up a better version of problem 1 and problem 2 yet. You can just skip those in your comments and focus on the later ones, and I'll give everybody comments on problem 1 and problem 2 over the weekend. So that's part of what we're on about. The second thing that I'm hoping that we're, and the reason why is because I would actually like us to be able to start talking and focusing on Wyngaard rather than looking backwards at the previous stuff, because we don't have too much time to talk about Wyngaard and talk about other things before the end of the semester. The other piece that's important is the feedback for me on the paper project, which also I will get to everybody by the end of this weekend. So all those things will happen over the next couple days. Are there any questions about that? Okay, great. So let's remind ourselves where we were picking up. I want to start the discussion following in chapter 9 of Wyngaard about the atmospheric boundary layer. And but remember, at the end of chapter 8, the equations of atmospheric motion, and it's really the equations of the atmospheric boundary layer, we ended up looking at this set. And these were very similar to the Boussinesq equations that we saw in Vallis, with a few small differences. So let's remind ourselves of those before we move on, because what we're going to do to talk about the atmospheric boundary layer is to look at some of the scaling relationships that arise from these equations. So here, remember, Wyngaard uses this tilde notation to mean the total turbulent velocity, which includes both a mean part and a turbulent part. And he uses so he's got a bunch of different variables here: the velocity, the pressure, the virtual temperature, but also the potential temperature. And remember, the virtual temperature, I'll show you in a second what that is. So the equations for the mean flow then look like this. They have a regular old material derivative. They've got a Reynolds stress. They've got a pressure gradient. They've got Coriolis. They've got a virtual temperature buoyancy. And they have it's Boussinesq or anelastic, and that the mean of velocity is non-divergent. We went over, remember how the Einstein summation means that this is actually a divergence rather than just a direct derivative in one direction. And then the last piece here is the transport of potential temperature looks like this, and the transport of the mixing ratio of any conserved constituent looks like this, and one of them that's very important is going to be the humidity. Along with those mean equations, we also have a subgrid set of equations because we needed to predict those second moment pieces. And so if we look at for example, the Reynolds stress, the IK component of the Reynolds stress, it has a mean gradient production, or sometimes we call this the shear production. It has a transport term, which depends on the triple correlation, which is not something that we know, but it is something we could measure. If we wanted to write an equation that governs this, we would need, that's the turbulent closure problem. We would have to write an equation that has a triple product. That's a mess. And it keeps going because the triple product would have a fourth product in it, etc. There's the pressure gradient interaction. There's the Coriolis force. And there is the buoyancy production. We get two terms in the Coriolis force because you symmetrize. You have to make sure that you get the symmetric part right. This is the U dot grad in both the M direction and the K direction in order to get this term. And similarly, the buoyant production looks like it has two different components, but look, here's one in the I direction and here's one in the K direction when the I and K is alternating. So in order to get the I-K symmetry we need for this is symmetric in I and K. We have to have two terms in the buoyancy production, two terms in the Coriolis. And in the viscous dissipation, on the other hand, assuming isotropic viscous dissipation, we get just a Kronecker delta, which is already symmetric, times the dissipation rate. We could also do the same game for the turbulent transport of a scalar, like the mixing ratio, and we get a term like this with the pressure gradient interactions, turbulent transport, mean gradient production, Coriolis, buoyancy production of the conserved scalar. And so studying these different turbulent terms, looking at all these covariances that appear in these equations is kind of the game of studying the atmospheric boundary layer turbulence. And think about their implications for the mean equation. You might say, why do we care about the turbulence itself? And we might not care about a particular cloud or a particular eddy, but we certainly care in bulk about what they do, and that bulk representation of what they do comes back through the Reynolds stresses and the covariance of the tracer and the velocity. Okay. So to jump on to chapter 9, the atmospheric boundary layer. In a boundary layer in general, in a fluid, we imagine that it's something like this, a flow profile where there's flow over a boundary. And this boundary could be a land boundary, it could be a solid boundary, the sidewall of a tank or the bottom layer of a tank in the lab, or it could be land, it could be ocean, could be a forest canopy, could be an urban environment, all kinds of different things all would come into a boundary layer conception. The main dynamics of a boundary layer are that there's a finite width to a boundary layer because the conditions that govern the free flow away from the surface are different from the conditions that arise when the frictional or turbulent terms become important in order to satisfy the boundary condition here at the bottom. So if we scale the equations and find some depth scale for the boundary layer, that would be the scale over which those extra terms might be more important. This conception was really developed for a laminar boundary layer where you can solve everything and think about the matching conditions between a viscous boundary layer and a relatively inviscid interior. So here you can neglect the viscous terms. Here you definitely can't. And because the viscous terms have a higher derivative in them than any other terms in the equation, they're the ones that require this additional boundary condition of either slip or no slip. This is illustrated here to be a no slip boundary condition. A lot of the times we think of no slip as being the true boundary condition because that's what a viscous fluid does. But we'll come to think a little more broadly about it as maybe a imposed stress boundary condition in a turbulent layer in a little bit. Because when we don't really resolve this microscalar, when it's actually kind of a rough boundary, thinking of it as no slip might not be the right thing to do. It may be better to think of it as a rough boundary contained within a log layer, like we did in the discussion of the log layer last time. Acoustically, you can actually watch the evolution of the boundary layer. So this is an example, and so notice it's going from about 200 meters to about 400 meters. And typically a boundary layer might go from tens of meters or even meters on a really warm, calm day up to hundreds of meters or even kilometers. And you can see that there's some variation in time, pretty substantial variation in the depth. And there are even things like this, detached turbulence, which, it's not clear what kind of a structure that is, but this is a really complicated thing. The evolution of both the thickness of this boundary layer and all these structures within it is what we're really thinking about when we think about boundary layer turbulence. You can see that the time scale here for the evolution is kind of in hours, and these features within the boundary layer might be much faster. We will think about whether there is a fair separation in time between the evolution of the boundary layer and the evolution of the features within the boundary layer. That's one of the key conceptual simplifications that allows you to make a real turbulent boundary layer mathematically look something like this idealized laminar boundary layer. So there are a few important features of the boundary layer. You can think of it as having continuously provided turbulence. So the boundary layer and the mixed layer might be quite different in that sense. We think of the boundary layer as being the one where the turbulence is, and the mixed layer being the one where the tracers within that layer are homogeneous in the vertical direction, well mixed. So sometimes the boundary layer is called the mixing layer, and the mixed layer is called the mixed layer, to get that distinction. When we do averaging of the turbulence, so you can imagine here, this interface has lots of high frequency variations as little plumes are kind of reaching the top. If we were to average over this layer, there would actually be kind of a thick, marginally in the boundary and marginally in the free atmosphere boundary layer. That's sometimes called the transition layer, or sometimes called the interfacial layer. But really, if you look, you can even see these little plumes. The real structure is quite thin and narrow. So if you were to take a particular, a single sounding of this boundary layer, you would see very thin structures, but those structures are turbulent. So in the averaging procedure, you mix up those thin, highly variable stuff into kind of a mushier layer where those features are lost in the averaged equations. One really important or interesting discussion to think about, and this touches on one of the homework problems that we talked about for the which is coming, is to think about what the direction of flow is within the boundary layer. And this is kind of an interesting example, maybe the cleanest example, which is a nice reason why Wyngaard begins with it, as to how the turbulent stresses come into play. So if you throw out the turbulent stresses and take our normal assumptions of small Rossby number, etc., for the mean flow, you get a geostrophic balance like this. And one of the things about the geostrophic balance is that this term is perpendicular to both the direction of the rotation axis, but also the flow direction. So if you dot this equation into the flow direction, this term vanishes because it's perpendicular to the flow direction, but this term has a u dot grad p equals 0. And so that means that the flow is not in the direction of the gradient of pressure. The flow is along the isobars. And we talked about that before when we talked about geostrophy and ballast, and that we made them, we talked about the pressure being the stream function for the geostrophic flow. This is just a different way of thinking about that. The flow is aligned along the isobars. But what happens if we include the turbulent stresses? So rather than this equation, we have one here that has the Reynolds stresses in it. If we go through the same exercise and dot into UI, big capital UI now, so because UI and UK in this term are symmetric in I and K, but epsilon ijk is anti-symmetric, that means with similar kind of tensor manipulation that this thing vanishes, or we could say it's just the same as dotting into the cross product up here. But UI.grad P now has something it could balance against. In fact, you get an equation that looks like the Reynolds stress dotted into the mean balances the cross isopycnal flow. So if there is a non-trivial Reynolds stress, then there can be cross isopycnal flow. Or if the boundary layer is turbulent, you don't necessarily have to have geostrophic flow. So we kind of hinted at this in our Ackman layer discussion, but there we used an eddy viscosity. This is sort of a more generic formulation of how to think about the fact that the flow in a boundary layer doesn't necessarily align with the flow, the geostrophic flow in the free interior. So that's a useful conceptualization, and this doesn't require the assumption of eddy viscosity in any way. In fact, one of the examples that Wyngaard goes on to talk about is forming the energy equation from this. And now, so here we have a term that's like a transport of turbulent energy. This one is the shear production term. So this is the transfer term between the mean shear and the turbulent energy. And then this one is the one that is the pressure work. So this is the one that comes from this one, from dotting it into the UI direction. So here again, cross isobar flow could be balanced by either of these two terms. If we integrate this over a large volume, this one is inside of a total divergence, so this one goes away, but this one does not. So now you see that in fact shear production is the thing that is allowing cross isobar flow. So if shear production is ongoing, the cross isobar flow can go. It could also, the turbulence could be getting energy from buoyancy production if it likes, which might drive up, even more substantial Reynolds stresses here than you might get from this term alone. So you could in fact end up with a more vigorous cross isobar flow. Are there any questions on that? Okay, so a few other observations about the atmospheric boundary layer. If you go through the scaling, which is one of the homework questions, to figure out the Rossby number that's relevant for the turbulence equations, not the mean equations, but the small scale flow equations, the Coriolis term tends to be small. The depth varies, as we said, from maybe meters to kilometers. There's a large diurnal cycle in the boundary layer. Frequently, so there's a variation in the winds, but not really so much the winds aloft as the winds at the surface. The variation in diurnal forcing really has a lot to do with the heating. And so this little energy budget model is helpful to think about when you're thinking about the heating. Solar shortwave radiation is coming down from the sun. It might be absorbed by the atmosphere, but the atmosphere is relatively transparent, so most of this makes it to the surface and warms up the surface. Long wave radiation is also coming from the atmosphere, from the clouds, based on their temperature and going downward. Sometimes it's called downwelling radiation. And the surface itself has a temperature, so it is acting like a black body and radiating upward. So there's an upward and downward long wave radiation contribution, which depends on the temperature of the surface and the temperature of the atmosphere above. And then there is also a heat conduction between the atmosphere and the surface. And that heat conduction could be sensible, temperature to temperature contact, or actually, if we're thinking about virtual temperature here, then it could also be latent heat exchange. So evaporation of water at the surface tends to bring latent energy exchange between the two. And then a small amount in over land, but none of the energy could be lost from this surface element down through into deeper soil. In the ocean, this same shortwave, long wave, sensible, and latent heat fluxes are important at the surface, but you can actually have stronger entrainment or vertical velocities in the ocean, which can make a convective contribution to the ocean response and make this budget look a little bit more complicated. But what you tend to get is, so as the shortwave radiation is coming and going from day to night and day to night and day to night, the temperature of the surface is changing. And so sometimes the surface is actually colder than the atmosphere above. And sometimes the temperature at the surface is warmer than the atmosphere above. And so instead of our normal temperature lapse rate, like we talked about last time, which was here, oh, that's the scale height for density. We actually talked about, there we go, the temperature lapse rate. If we just had an ideal gas hydrostatic isentropic with no forcing, we would expect an exponential decay of temperature with height, with this scale height, about 1 degree Kelvin per 100 meters. Instead of that, we can find things like this, where you have a temperature inversion, which is, rather than a steady decrease with altitude of temperature, you might have a warmer temperature aloft. And what that means is that if one of these parcels ascends, maintaining its temperature, it would find stable stratification above the boundary layer. And so this acts as a barrier, a stratified free atmosphere, or cap on top of the boundary layer turbulence. So even though you might have an unstable atmospheric boundary layer because the surface was warm, causing convection, or the surface was moist, causing latent heat flux, and then virtual potential temperature buoyancy and convection, frequently that convective flow would actually bang into this inversion and then be trapped in between. At night, this surface element tends to be cooler, and so you tend to have pretty much a uniform, stable, more stably stratified layer all the way top to bottom, and so it tends to be only weakly turbulent. So another way that you could get a stable boundary layer is if you have air that's kind of in this sort of a profile. Here's the inversion, and here's the profile of temperatures as you go down to the warm land below. As you go, oh, if that was advected over cooler water, you would start to grow a stable layer, because the cooler water would start exchanging in air sea heat fluxes, warming up the water with the heat from the lower atmosphere. And so you might get cold air here at the bottom, and then it's stably stratified now all the way from the capping inversion down to the base of the mixed layer, to the base of the atmospheric boundary layer. Another way that you could get it is if the air from above was actually mixing and entraining down into your boundary layer, which might be happening if the boundary layer was getting deeper, growing in height. Then the heat fluxes would be something like this, and you would actually end up with a stable temperature profile from virtual temperature profile from the inversion all the way down to the surface. So you might get something like this, where the inversion is sort of taken over all the way through, stabilizing the boundary layer. Now, this doesn't mean that the flow is totally stable. You could still have the generation of turbulence from the shear stress at the surface, which would then, but the turbulence would be damped by the buoyancy production. So in fact, Wyngaard goes so far as to call it buoyancy destruction in that case. When you have a stable stratification, the turbulence is inhibited by the boundary layer, by the buoyancy terms in the Reynolds stress equations and the buoyancy flux equations. And so if you think about the kinds of structures that are the biggest ones, you think about them being kind of like this. Here's the inversion up at the top of the boundary layer, and you have these big overturnings, which might be cloudy, because as you're lifting the air up, if it's moist air, as it gets higher, it's getting colder temperatures, the pressure is going down, the density is going down. You might end up precipitating, you might end up just switching from a vapor form into a cloud form, which might not be precipitation, but you have this kind of structures where they're absorbing warm, moister air at the surface, carrying it aloft, reaching the top of the capping, and going back down. It's in fact the case that in both dry and moist boundary layers, the updrafts are more intense than the downdrafts. So not only the variance of vertical velocity, the vertical velocity squared, or the RMS vertical velocity is important to think about. That's the one that goes into the Reynolds stresses. But the skewness, the vertical velocity cubed, tends to be positive, which means that the updrafts are more intense than the downdrafts. And we'll see in the oceanic boundary layer that the downdrafts, the downward currents, especially in Langmuir turbulence, tend to be more intense than the upward turbulence, return flows. So in the ocean, you tend to get a negative skewness. In the atmospheric boundary layer, you tend to get a positive skewness of vertical velocity. So one more feature. So if we think about this little heating element, we might think about what the fluxes are from the surface to the atmosphere above. So this is the buoyancy fluxes. And so at night, between sunset and sunrise, this has the flux going downward, warming the surface. But during the day, the surface is warm and the flux is going upward. And so the turbulent fluxes are going between the stable nighttime boundary layer, where they are negative and relatively low effectiveness, versus the daytime when convection is very strong. In the ocean, you have a very similar diurnal cycle. Wyngaard talks about the fact that the ocean might be neutral. That is the brief period in the atmosphere where you're switching from the stable boundary layer to the unstable boundary layer. There's an idea that you might be neutral, where the buoyancy forces are really small. So here you're very briefly passing through it here, and here you're very briefly passing through it here. Actually, if now that we have better measurements of the ocean, I would say it's fairly clear that even in the ocean, the neutral case is relatively uncommon. In climate models, or in models that average over many days, a neutral profile is taken sometimes as the typical profile, but it's kind of a funny thing to do, because it's pretty clear that if you average over this stable nighttime layer and unstable daytime layer, you don't end up with something that is zero flux. You end up with something that is very strongly dependent on the funny average of how tall this is versus how negative this is. We'll get back to that as we think about the longer time scale effects. And remember, the temperature that's important for this is really the virtual temperature. These fluxes might be driven by either latent heat fluxes or sensible heat fluxes from the surface. One way to think about the balance between advection or inertial forces, the Reynolds stresses and the shear production that tend to produce turbulence from shear, and these buoyancy forces, which during the daytime tend to accelerate the amount of turbulence, but during the nighttime reduce the amount of turbulence, is to think of the Richardson number. There are three different Richardson numbers that are useful for thinking about a turbulent boundary layer. The one we've already discussed for the Kelvin-Helmholtz problem, or the stratified Kelvin-Helmholtz problem, was this Richardson number, which is sometimes called the gradient Richardson number. And it gives you basically n squared, and this is the atmospheric version of n squared, so the Brunt-Weissela frequency in the numerator, and then du dz in the denominator. So when it's more stratified, n squared goes up, and this number gets gets larger, and when it's more shear, more tendency to overturn, this Richardson number gets smaller. So typically turbulence happens when the Richardson number is somewhere between about 0.2 and 0.3, and in fact in the linear instability problem, the linear version of the Kelvin-Helmholtz problem, which we talked about a little in class, there is a Richardson number of 1/4 with 0.25 limit on when the linear instability can occur. But more generally, we might want to think about how much buoyancy there is per unit inertia. And so we could think of that in just a scaling. What's the scale of this? Well, it's G times some delta temperature over some background temperature over some vertical height. And this is some velocity scale over vertical height squared. If we cancel one of the vertical heights between these two, we end up with this formula. So this is called the turbulent Richardson number, and it basically measures how much buoyancy force you have versus how much inertial force you have, which if we think about it in terms of the mean, it's essentially saying how big is this term versus how big is this term. They could be of the same sign, that is, in an unstable boundary layer, this and this add together. In a stable boundary layer, they would be in competition. So you might want to think about the turbulent Richardson number as having positive and negative signs. For the moment, let's leave that aside because that's something that's a little more complicated. It'll be more natural when we talk about the Monod-Nabokov depth. The flux Richardson number is similar, except it is more explicitly thinking about, rather than the mean equation, the Reynolds stress term versus the buoyancy term in the mean equation, it's thinking about the buoyancy flux term in the perturbation and the turbulence equation and the shear production term in the turbulence equation. So if we think about that, it's this term, which is how much energy is either produced or destroyed by buoyancy, by the turbulent fluxes of buoyancy. This is when light stuff is going up and when dense stuff is going down. This tends to be producing energy. When dense stuff is going up and when light stuff is going down, this is the mixing term we talked about from Thorpe. And so this one is the one that is, and then it would cost you energy to do that mixing because you're creating potential energy at the expense of kinetic energy. And this one is the one where we're converting mean kinetic energy into turbulent kinetic energy. And if we think about the ratio of those two terms, we might talk about the fact that this one would be limited by, in a stable boundary layer, this one would have a limit, just as the gradient Richardson number does. And so in the stable boundary layer, if we in fact assume that that limit occurs for the flux Richardson number, this and that were about the same size, this term might scale like some typical velocity scale cubed. That might be the friction velocity. This one would scale like this kind of a product, which is a vertical length scale times the background gradient, and then another velocity, and then the scale factor to get the units right. If we set this one equal to this one, we find that there is a buoyancy depth or a buoyancy height in a stable boundary layer, sometimes called the critical scale. And this is the RMS of the vertical velocity. So the vertical velocity squared, square root, the RMS vertical velocity divided by the Brunt-Weissela frequency. So if the vertical velocity is very big, very turbulent, then this scale would be big. If it was not very turbulent, this scale would be small. So in the boundary layer, you can figure out what this is, and typically this one is dominating that. And in the capping inversion layer, this is usually pretty small, and so this layer ends up being actually only a few tens of meters deep. So when the plumes hit the top, they're actually suppressed in the capping layer, and within the boundary layer, n is very small, so this is pretty much the depth of the whole boundary layer. There's a lot of discussion within Wyngaard about whether it's reasonable to start doing these budgets and neglecting the horizontal fluxes. And in the Kansas experiment, this famous experiment over a cornfield in Kansas where they thought that the boundary layer would be as boring as possible, even there they found that the time scale between the turbulent time scale, that is how long it takes for an eddy to overturn the whole of the boundary layer, versus the evolution time scale of the boundary layer depth, wasn't always cleanly scale separated, particularly due to the diurnal changes we've been talking about. Secondarily, there were kind of mesoscale features and other things that were being advected into and out of the domain of interest. Gusts essentially, and those were also affecting whether or not you were steady or not. So you can really only assume that there's a steady balance, that is where the DDT terms in the turbulence equation are negligible, or in the mean equation are negligible, and the DDX, the horizontal gradient terms, are negligible. It's something a balance like this. You'd want to evaluate whether the changes in the fluxes versus the advective time scale, whether that was small or not. And you can do the same thing for the homogeneous assumption. So homogeneous, remember, is uniform in space. Stationary is uniform in time. And the skewed distribution we've already talked about. One of the really interesting violations of homogeneity we've already talked about, and we're going to come back to when we think about submesoscale ocean flows, but it's also true of mesoscale atmospheric flows. And that's, what if we have a geostrophic balance that is superimposed on our mean system? So we have some pressure gradient in the horizontal, in the x direction and the y direction, driving a geostrophic flow. That geostrophic flow is we think of it as being above the boundary layer, but these pressure fields might also penetrate into the boundary layer. What do they do? A convenient way to rewrite the mean momentum equations in the boundary layer is to so we're within the boundary layer, so we've got the turbulent transport terms as well as the terms in the geostrophic balance, and he's written the pressure gradient, he's just rewritten it as a geostrophic velocity. So the net velocity, the velocity minus the geostrophic piece, comes out to be cleanly like this, and it would be you could potentially have an acceleration of the flow within the boundary layer, and then the Reynolds stresses. If we were stationary, we could neglect these two, and then we're back to the idea that the flow might cross the isobars, might deviate from geostrophic flow in the presence of turbulent stresses. So that comes back to that same theme that we talked about before. So what if there are horizontal temperature gradients, not just horizontal pressure gradients? What if these horizontal pressure gradients are coming from horizontal temperature gradients, not above the boundary layer, but within the boundary layer? What does that mean? Well, we've actually already done this calculation before. We know what happens if we have pretty large scale horizontal temperature gradients. The first thing we can find is if the length scale is pretty big, we can be hydrostatic instead of non-hydrostatic, and so we can relate the vertical variation of pressure to the variations in temperature. And then if we differentiate this with respect to x and y, we can figure out where these horizontal pressure gradients are coming from. And not surprisingly, what we find is it's not quite as obvious as written this way, but this is basically the atmospheric version of the thermal wind relationship. We have that there is a vertical gradient in the geostrophic velocity that's produced by the horizontal deviations in temperature, and then this piece has to do with the fact that the density is decreasing with altitude as well because of the scale height of density in the atmosphere. So this is a compressibility term. So this is thermal wind plus a small compressibility effect. And if the depth scale we're thinking about here is small compared to the scale height of the atmosphere, which is usually typically true in an atmospheric boundary layer that's maybe 1 kilometer or less versus a scale height that's 10 kilometers or so, then this term is negligibly small, and then we're back to the regular old thermal wind relation. So and in the ocean version of this, we won't even have this compressibility term, we'll just have a thermal wind relation. But look at what the thermal wind relation is saying. It's saying if we have inhomogeneity or heterogeneity in the temperature field, we expect to see other shear in the boundary layer that doesn't have anything to do with these stresses. This shear is the baroclinic shear. So that's something that's important, that's on as the scale gets large enough that the horizontal heterogeneity of temperature and also pressure become clear in the boundary layer. The Ackman solution is also, this comes out if we want. So here's the Ackman solution as Wyngaard writes it. He does a nice job, actually maybe a cleaner job than Vallis does, of the question that we addressed in the first couple of homework problems, which is what is the divergence of the horizontal velocities implied by, what does that imply if you have a stress that's not constant? You tend to get a vortex stretching term that's in balance with that in the vorticity equation. That vortex stretching term is really coming from the turbulent stresses, or the turbulent stress divergences, I should say, that are implied by this change in the Ackman shear. Or thinking of it in terms of the stresses, you can see that the stresses, the derivatives of the stresses, and this is like the curl of the wind, or the curl of the surface stress, is giving you this F vertical velocity at the top of the boundary layer. So if there is a curl in the surface stresses, there is a vertical velocity at the top of the boundary layer. Or writing it in terms of a drag coefficient and the vorticity aloft, which is giving you the stresses of the surface, the vorticity is proportional to the vertical velocity, like this. So that the vorticity and vertical velocity at the top of the boundary layer are related. And that's really important because if we think about it like this, here's our boundary layer, here's our surface stress. If we have a positive vertical velocity at the top of the boundary layer, we are stretching and accelerating the vorticity within the boundary layer. So if there's a positive vertical vorticity above the boundary layer, we're doing a stretching of the boundary layer and a contraction of the vortex that's sitting on top of the boundary layer. If the other way around, if we have an anticyclone above the boundary layer, then we tend to have a compaction in the boundary layer and a stretching of the vortex above the boundary layer. And the funny thing about this is what this tells you is that the Ackman layer tends to eliminate any relative vorticity in the fluid above it. Or to put it simply, the Ackman layer is a damping layer. The Ackman layer damps vorticity. It damps vorticity through surface drag and turbulent transport of momentum. But even more simply, in the vorticity equation, it acts in such a way as to reduce the amount of relative vorticity. So whether it's cyclonic or anticyclonic, this stretching term here with the Coriolis F parameter in front of it gives you a counterbalance to the stretching and squeezing. So that's all I wanted to say for today. So are there any questions? And let me point out again that it would be really helpful if everybody does the reviewing of all of the questions except for question 1 and question 2 for tomorrow, so that we can just be done with that step and start thinking about the next problem set. Akash, did you have a question?
Yeah, in the chat box I have written a question that the Richardson number increases. Does that mean 2D turbulence sets in, or is there anything between 3D and 2D and Richardson number? Is there any relation or something?
That's an excellent question. So here, if we go back to the Richardson numbers, let's look at it. So if there was already turbulence and somehow you manage to increase the Richardson number, suppose you go over cold water on land, then that turbulence might still have some residual energy, but you would see it decay because it would cost buoyancy. The buoyancy term would be acting against the shear production. So you could imagine that it would be decaying in this overturning turbulence, the kind that has vertical fluxes and balance like this. So notice that this is a vertical flux, and this one would have a vertical component at least. Now, one of the things that's really interesting about 2D and quasi-geostrophic turbulence, which some boundary layer people don't even like to call it turbulence because it's so different in this respect, is you could have horizontal shear production. So if I and J are in the horizontal and the gradients are also in the horizontal, then that would be something like the two-dimensional Rayleigh criteria that we saw before. You could produce turbulent kinetic energy without any vertical motion at all. So it could still be turbulent, but it wouldn't be turbulent to 3D turbulence. It would be turbulence in the directions perpendicular to the buoyancy. So mesoscale turbulence, submesoscale turbulence, geostrophic turbulence tends to be of that flavor. Where you have a large Richardson number, you still have turbulence, but the turbulence is drawing its energy from a different mechanism than what it does in a 3D turbulence setting, where you have to work against the buoyancy destruction in order to preserve isotropic turbulence in the face of stable stratification.
So for something like geostrophic turbulence, these two effects are coupled. They are not coupled, as in the shear production and buoyancy destruction.
Yes, so for barotropic turbulence, or equivalent barotropic turbulence, it really doesn't interact too much at all with the buoyancy production. It has everything to do with the transport along the buoyancy surfaces rather than across the buoyancy surfaces. So mesoscale eddies tend to have velocities that are just aligned with the density surfaces. And the same is true of atmospheric synopsis. Well, it's not true in the atmosphere in the same way because of the radiation and the deviations from conservation of buoyancy during flow. But in the ocean, away from where the radiation is warming and cooling things off, you just get flow along the density surfaces. And so it's turbulent in that direction, in a 2D sense, a quasi-geostrophic sense, but it is not overturning the buoyancy surfaces. So that's barotropic or equivalent barotropic turbulence, but there's also baroclinic turbulence, which is a kind of sideways exchange of density that allows you to extract buoyancy production, to extract energy from buoyancy production. Basically, imagine a three-dimensional process where the warm stuff is sliding on top of the cold stuff. We saw that in a couple of movies, but we're going to come back and talk more about it as we get to the submesoscale and mesoscale dynamics. In that case, you're putting warm on top of cold. You're not doing any vertical overturning to do it, though. You're just sliding them horizontally along density surfaces. But you still end up extracting energy by putting the warm stuff on top of the cold stuff. So that will be another mechanism where we can avoid this flux Richardson number constraint and still have turbulent motion or quasi-geostrophic turbulent motion at large Richardson number. And if you remember back to our derivation of the quasi-geostrophic equations, we talked about small Froude number or equivalently large gradient Richardson number. That everything we talked about in the QG equations is in this. All of these terms would be very, very large. So it would be stably stratified. It would not be turbulent in the sense of Richardson number below 0.2. So they say all turbulence can be extinguished, but what they mean is all isotropic turbulence, quasi-geostrophic and geostrophic turbulence would persist.
Oh, I see. Okay. Okay, that makes sense. Cool. Thank you.
All right. Thanks, everybody. See you later, and see you on Friday. And I'll give as many comments back as we can. So we'll be in touch.